This lecture we are talking about a new topic, gravitation. This is the second topic in A2 physics. Gravitation, as the name suggests, is about gravity, which is one of the most commonly known force around us, the most widespread, the most commonly experienced force in our life. This is one of those fundamental forces which is an active topic of research today. There is an ongoing research about gravitational waves, gravitons, but obviously we are not going to go in that detail at this stage. We'll talk about the basic work that Newton's completed on this topic, and even that basic work has been very useful because using that work we were able to develop all the satellites, and today all our space program is basically the result of those breakthroughs. That was the result of Newton's seminal work in this field of physics. The first important discovery of Newton's was Newton's gravitational law. Newton's Newton discovered that all objects attract each other simply because they had masses. This force, which is the result of their having masses, does not depend on their state of rest or of motion. It does not depend on whether they have any charges or not. It does not depend on their shape. It simply depends on the fact that the two objects have certain mass. This is not fully understood why this force originates, why two objects simply attract each other just because they have masses. As I said in the beginning, this is an important topic of research, and this is the general theory of relativity, gravitational waves, the particles believed to be involved in this force called gravitons. They are being searched for, but nothing is conclusive at this stage. So without knowing a lot about this force, we can talk about it at this stage. Newton's law of gravitation states that any two masses in the universe, whatever their shape and sizes, whatever their state of rest or of motion, they will attract each other with a force which is directly proportional to the product of their masses. That means the two objects are attracting each other with a force, and they attract each other with exactly equal and opposite force. I'll come to this later on. But this force is same as this force. This is the force with which this mass is attracting this mass, and this is the force with which this mass is attracting the other mass. So these two are equal and opposite forces, and if I take any one of these two forces as F, this force is proportional to the product of their masses. If I label them as masses M1 and M2, this force is directly proportional to their product. And this force is also has a relationship with their separation. If these two masses have their centers separated by the distance r, this force will be inversely proportional to the square of the distance between their centers. As I have tried to take the centers from this and the center to this mass, the separation is small r. If I combine these two, we can write this relation as m1, m2, the product, and r square, which is the square of the distance between them. So force is directly proportional to the product of the masses and inversely proportional to the square of the distance. By this fact, we mean if we double the distance, the force reduces to 1/4 of its original value. And if we increase the distance 3 times, the force reduces to 1/9 of its original value. In order to change this relation into a mathematical equation, we introduce a constant, capital G. The rest of the variables will be like this. And we have an equation which is the mathematical statement of Newton's law of gravitation. This is a new constant known as universal gravitational constant. Gravitational constant, you will have its value in the data booklet, and this will always be 6.67 into 10 raised to the power minus 11 in SI base units. And you can easily guess the base units: Newton, meter square, kg minus 2. This will be the value always given in the data booklet. So you will be using this equation for all those situations in which the force of gravity is to be worked out between any two masses, big and small. An important thing that I stated earlier, I will discuss that point in detail. If this force is same as this force, this means Newton's third law of motion is also at work here. If this mass exerts a force F1, 2, let's say, if this is the force that mass M1 exerts on M2, this must be the same force as the mass M2 exerts on mass M1. So these are two different forces. One is F12, the other is F21, but these two forces will always be equal in magnitude and opposite in direction. This means Newton's third law of motion is also at work when we talk about Newton's law of gravitation, because two equal and opposite forces are involved, and these are the forces which are acting on two different objects. They are not acting on the same object, so Newton's third law becomes relevant here. The second point is that gravitation is always attractive force, always attractive force. Gravitation is never a repulsive force. So when we try to show the forces acting on two objects, we always show in this manner the forces towards each other. and not away from each other. The third thing is, we always apply this equation on point masses. Point masses. Point masses mean either the masses should be very small in order for this equation to be mathematically accurate, or if they are large masses like sun and earth, like a satellite and a planet, they should be reasonably far away from each other. So point masses means two things: either small masses, or large masses with large separation. So this is the introduction of Newton's law of gravitation. I quickly repeat what we have talked about so far. Any two masses in the universe, big or small, at rest or in motion, they always attract each other with a force which is directly proportional to the product of the masses and is inversely proportional to the square of the distance between their centers. This statement is written in all books. It is written in all the website talking about this gravitation. So instead of writing the statement here, I'm trying to elaborate what this statement means. So that statement has two parts. One part is the masses always attract each other, and that force is directly proportional to the product of their masses. This is one part. The other part of the statement is that that force is inversely proportional to the square of the distance between the centers of those masses. So this is Newton's law of gravitation. When Newton's law of gravitation is applied to those situations in which a mass is moving in a circle around another mass, for example, you have a sun-earth system in which the sun is at the center and the earth is going around in a more or less circular orbit. In this situation, we know the separation between the two objects, which is the radius of this orbit, and that is almost 6,400 kilometers. This is 150 million kilometers. That was the radius of the Earth that I was talking about. This is the radius of the orbit when Earth moves around the sun, and the separation between the two objects is 150 million kilometers. That means 1.5 into 10⁻11 meters. With this large separation, we know the Earth takes exactly 365 days on average, 365 days on average to complete its orbit, to complete one round trip. If I change this time into seconds, this comes out to be 3.2 into 10 raised to power 7 seconds. That means we can calculate omega easily from this information. 2 pi over t will be our angular speed of the earth with which it is going around the sun. And with this, it comes out to be 1.96 into 10 raised to power minus 7 radian per second. This is from this equation that I was able to calculate the angular speed of the earth. If I use this information and this and the mass of earth is also known, this is 5.97 into 10 is power 24 kilograms. Using all this information, I can calculate the force, which is mr omega square. Simply the centripetal force needed to hold the earth in this orbit. This force must be this mass used, this radius used, and this value of omega used. When I use all these values in this equation, I get a number approximately 3.5 into 10 raised to power 22 newtons. This is something we have calculated using our understanding of the circular motion. I have not used the Newton's law of gravitation yet. But what if I want to calculate the same force using the Newton's law of gravitation? Then I will be using F equals G mass of sun, mass of earth divided by the square of the distance between the centers of the sun and that of the earth. If I use these values now, G is 6.67 into 10 raised to power minus 11. Mass of sun is 1.99, 10 raised to power 30. Mass of earth, as already used, is 5.97, 10 raised to power 24 kilograms, divided by this distance squared, 1.5 into 10 raised to power 11 meter squared. When I simplify, this number comes out to be 3.5 into 10 raised to power 22 Newton. So this and this comes out to be same. That means whether I calculate the force needed for this object we know as Earth to move in this stable orbit, this is the force needed for that purpose. We calculated this force using our understanding of circular motion. But when we use the same force using Newton's law of gravitation, which simply means this equation, which does not tell us whether the object is in motion or not, we simply know that these two are the masses which are at this distance from each other, and these are the two masses involved. This is the universal law of gravitation, which gives us the same value that we have used earlier using the idea of centripetal force. So this is the importance of law of gravitation, and this is how we can work it out. We will go further a step and see what else we can calculate once we know this expression and once we know that this is the same force which is playing the role of the centripetal force. Now that we know that sun with earth going round and round makes a stable orbital system, we can apply law of gravitation to the circular motion and see what expressions, what useful quantities we can calculate from it. I mean, force of gravitation can be equated to mv square over r. This is g mass of sun, this is mass of earth over r square. This is also mass of earth. So this is mass of earth v square over r. It is easy to see that this mass gets cancelled from two sides. This v is the orbital speed. It is the speed with which this earth is moving around the sun, and this v is clearly equal to g into mass of sun divided by the radius of the earth, which means the separation between the centers of the two objects under root. This is the expression for the orbital speed. Orbital speed. So if you are required to draw an expression, derive an expression for the orbital speed of any mass moving in an orbit about another mass, you can use this standard technique. You equate the gravitational force between them to the centripetal force, which simply means that gravitation or gravity is playing the role of the centripetal force in this case, because v is that speed with which the object should be moving at a uniform rate around that bigger mass. So this will give us what should be the orbital speed. If I use the values here, the value of g, the mass of the sun, and the separation between the two, I will calculate this speed easily. So there are questions in the exam where these values are given for different planets, for different stars, for even the artificial satellites that we have launched, which are moving around the earth. So for all those systems, we can calculate the orbital speeds easily with this equation. So this is one example where law of gravitation can be used with the circular motion, with the centripetal force, to calculate a quantity. If I start with the same g m m over r square. This time I have used one small mass and one large mass. In order to use the indices or the subscripts there, we can write the expression in this way. And I equate this to mr omega square. This will always be the equation when we know an object of this mass is moving in a stable orbit around this mass, the bigger mass, with this angular speed omega. It may be a planet going around the sun or a star. It may be a satellite going around the earth or any other planet. We will always be using this equation if we want to equate the gravitational pull on that mass, the small mass by the bigger mass, and this object is moving in a circular orbit. If I cancel this m from two sides and further simplify, this is gm equal to r cube omega square. This is another standard expression which gives us an important insight into what is the behavior of the bodies that we observe in the heavens. This is the relationship between the radii of the orbits and their angular speeds. So we'll see here that this will always be a constant. R cube omega square is always a constant because that constant involves the product of two things which remain unchanged. If this is the mass of a sun, let's say, this will be the same value for all planets, and this is the constant known as the universal gravitational constant. So the product of these two constants will always be the same value. So this product, which is the product of the radius of the orbit and the angular speed of the mass, this will always be the same number. I give you an idea through a figure here. Let's say this is the sun at the center, and this is one planet going around this, and this is another planet. The radius, which means the distance between the centers of this mass and the sun, is r1, and omega for this is omega 1. Let's say this is at a certain other distance r2 from the sun, and it is moving at the angular speed omega 2. If I apply this equation on these two systems, it is easy to see that I will be writing is omega 1 square r1 cube, the same answer as omega 2 square r2 cube. That means whenever you write this product for any planet, you will get the same answer. So this was an important discovery by Newton. It was earlier studied by other scientists known as Kepler. So this is sometimes referred to as Kepler's law. One more thing that we can calculate using this expression is the acceleration due to gravity of any planet, of any satellite, of any star, and that again is a very simple technique. Suppose we want to calculate acceleration due to gravity. That also means gravitational field strength. We refer to it as small g, and we already know for Earth its value is 9.81 meter per second square for Earth. Sometimes we can find the value of gravitational field strength of a certain planet using the same expression we have just used for other two purposes. This time, I'm assuming that this is the planet and there is a certain mass placed on its surface. From this center to the center of the planet, the distance is nearly equal to the radius of that planet. This is the mass m, and the mass of this planet is capital M. Obviously, Gmm over capital R square is the force between these two masses. One is very large mass, which is a planet in this case. The other is a very small mass placed on the surface of that planet. And the separation between these two masses is equal to the radius of the planet that we are talking about. If I equate this force to that simpler mg that we believe to be the weight of that mass m that we have placed on the surface, and these two expressions should be same essentially, because this is the force which we believe is the weight. And here we are ignoring the spin of that satellite, because that will come in later on. That makes a slight change to this picture, but for practical purposes these two expressions can be equated. If I cancel this, the value of g should be g capital M, which is the mass of the planet, divided by the radius of the planet squared. So this expression is always used for calculating the gravitational field strength. If it happens to be the Earth, then this is the mass of the Earth. The value of g is 6.67 into 10 to the power minus 11. Mass of Earth is nearly 6 into 10 to the power 24, and the radius of the Earth is 6,400 kilometer. So this is in meters, and this all squared. When you simplify this all, g will come out to be 9.81 meter per second square. So these are some of those quantities that we can work out using Newton's law of gravitation applied to the circular motion. A few more things will be discussed in the next lecture. We'll continue talking about gravitation in the coming lectures. Thank you.